Hi, I'm Malsha Perera from the Department of Electronics and Telecommunication Engineering, University of Moratuwa, Sri Lanka. I'm a leading author of the paper titled A Joint Convolutional and Spatial Quad-Directional LSTM Network for Phase Unwrapping. In our study, we consider the phase unwrapping problem, where the objective is to recover the true phase from the wrapped phase. And in the first figure, we can see a one-dimensional true phase signal, and the second figure shows the wrapped phase of that true phase signal. And the wrapped phase is confined to the interval between -5 and +5. To obtain the wrapped phase, we can use the angle of the complex exponential of the true phase. In order to obtain the unwrapped phase from the wrapped phase, we have to add an integer multiple of 2,5 to the wrapped phase signal. And the integer multiple k is also known as the wrap count. And these concepts can be extended to the 2D scenarios as well, such as images. And we can see a wrapped phase image and its counterpart of true phase image. And phase unwrapping is convenient under ideal noise-free conditions. However, at the presence of noise, phase discontinuities, and rapid variation of phase, the problem becomes challenging. And in the existing studies, there are two traditional approaches have been used, and one is the path following algorithms. The quality-guided phase unwrapping, QGPU, branch cut algorithms are two examples for path following algorithms. And the other traditional approach is the minimum norm-based algorithms. There are several drawbacks of these traditional approaches. One is that they are computationally inefficient, and also they are less robust to noise. In the recent years, several studies have used deep learning-based approaches to solve the phase unwrapping problem. Mostly they have used convolutional neural networks, or CNNs, and there are two types of CNN-based approaches. One is to formulate the phase unwrapping problem as a semantic segmentation task, where the wrap count, or the K, is predicted from the network. FaceNet and FaceNet 2.0 are examples for this type of CNNs. And the other approach using CNNs is to formulate the phase unwrapping problem as a regression task, as done in ReRectel. In this task, we directly predict the true phase from the given wrapped phase. However, there are several drawbacks of these existing deep learning-based approaches as well. They are also less robust to noise. And if we consider a phase wrap signal or image, we can see that there are global spatial relationships within that image. However, CNNs ignore global spatial relationships in an image. Therefore, the previous deep learning-based approaches, which use CNNs, have ignored these global spatial relationships within a wrapped phase image. Also, these existing methods are highly data intensive. Therefore, it's not suitable to be applied in real-world applications. Also, they have not used appropriate loss functions in their studies. Also, reframing the problem as a regression task has not been explored well in the existing literature. Our main contributions in this work is that we introduce a convolutional neural network architecture modeled after UNet, which consists of the SQD-LSTM block, which is the spatial quad-directional long short-term memory block, in order to model the global spatial dependencies. And also we formulate the phase unwrapping problem as a regression task, and we also use the problem-specific composite loss function in our work. If we take a look at our network architecture, we give the wrapped phase image as the input to our network, and we obtain the predicted true phase as the output from our network. And our network consists of encoding pathway and also decoding pathway. And these two pathways are connected using skip connections. And these two pathways consist of convolutional blocks. as shown in the diagram. And at the end of the encoding pathway, the output is sent through SQD-LSTM block, which is placed in order to help the model to learn the spatial global dependencies within an image. And the output from this block is then passed to the decoding pathway to obtain the final output. So if we take a look at the SQD-LSTM block, there are 4 LSTMs in this SQD-LSTM block, and we give 4 different sequences as the inputs to these LSTMs, and these sequences are obtained by traversing along the input feature map along 4 different directions. And the LSTM outputs from the sequences that's obtained by traversing along the horizontal direction is then concatenated and fed into a convolutional layer in order to model the local association of features. Similarly, the same thing is done for the 2 sequences obtained by traversing the input feature map along the vertical direction, and the LSTM outputs are concatenated and fed into the convolutional layer. And the output from the convolutional layers are concatenated to obtain the SQD-LSTM blocks output. So we use the LSTM blocks in this LSTMs in this block in order to allow the model to learn the global spatial dependencies in the given input feature sequence. So this is important when it comes to solving the phase unwrapping problem. As I mentioned previously, we are focusing on using a regression-based phase unwrapping solution. So our go-to choice would be to use a mean squared error loss function in our work. However, as I mentioned earlier, the wrapped phase can be obtained by the angle of the complex exponential of the true phase, and it follows from this equation that there are infinite solutions that give rise to the same wrapped phase. Therefore, the loss function should allow for multiple solutions at convergence while increasing the similarity between predicted phase and the true phase. In order to facilitate these conditions, we introduce a composite loss function, including the two losses, variance of error loss and the total variation of error loss, denoted by these 2 equations, so that we can satisfy these 2 conditions. So I would like to invite my friend Ashwin to discuss the rest of the presentation.
Hi, my name is Ashwin Silva, and I'm also a junior lecturer at the Department of Electronics and Telecommunication Engineering at the University of Moratuwa, Sri Lanka, and I'm also a leading author of this paper. Let's have a look at the experiments section of our paper. So for the experiments, we primarily created 2 datasets, one noise-free and noisy dataset. So these datasets contained 256 by 256 synthetic phase images, and they were created by randomly setting parameters on this equation that you can see in the screen. So here you can see that we have added ramp phase randomly, and also a constant phase, and also apart from that, quite importantly, the several randomly functioned and shaped Gaussians were also distributed among the regions of this image as well. So this was to give give a sense of arbitrary images to arbitrary objects to our images. So that was the purpose of adding these Gaussians, so that the networks would learn to unwrap more generalized phase, wrapped phase. And then we use the train test split of 5,000 to 1,000. And as you can see, it is not a great figure as usually used by deep learning architectures. And also, apart from our proposed network, we also implemented Reuertel's network, FaceNet 2.0, and QGPU as well. And among these, FaceNet 2.0 is the state-of-the-art deep learning architecture available for phase unwrapping at the moment. And QGPU is another quite successful algorithm which does not use deep learning to unwrap phase. And then apart from these networks, we also implemented a unit with MSE loss and a unit with LC loss, which is the composite loss function that we created to assess the significance of our SQD-LSTM block and our composite loss function. And as the performance metrics, we used normalized root mean square error for our results, and it is defined according to this equation. So the results can be seen in this table. So first off, we have the units with MSE loss and our proposed loss function. So here you can see confirming our hypothesis about the MSE loss. It has performed poorly in our dataset for noise free. But when we add the composite loss function which we proposed, you can see that the error has drastically reduced, and that shows that our loss function is quite adequate for this problem. And also looking at the results from the contemporary methods, you can see that for noise-free dataset, the QGPU performs quite better, but at the same time, the proposed method works well on noise-free dataset as well. But when you move into the noisy dataset, you can see some drastic changes here, and while all the other methods are performing quite poorly, our method was able to prevail in noisy dataset, noisy image phase, unwrapping noisy wrapped phase images as well. So apart from these results, we are also reporting the computational time during inference. So here you can see to how much time each method expends to unwrap wrapped phase. So here you can see out of all these methods, our method has accomplished the lowest computational time during inference as well. And these are some visual results that we have reported. So here you can see noise-free images and how the results from the unwrapping methods have performed. So here you can see the proposed network quite similar to the true phase and also RioETL QGPU as well, but PhaseNet and other methods have not performed quite well in that regard. And then when you slowly start to add noise, here you can see that the proposed method still holds on quite well, but you cannot say the same for other methods, as you can see that when you add noise to the wrapped phase image, they become quite distorted and they deviate from the ground truth, which is a true phase. And here you can see some statistics pertaining to the different noise levels that we have added. So here you can see that other methods, they perform quite poorly during when you have severe noise levels present in the wrapped phase. But you can also observe that the proposed method keeps a steady performance for varying levels of noises, thus giving a sense of stability to it, and also showing that it can unwrap wrapped phase even in noisy conditions. So looking at these results, we can come to several conclusions. And first up, we have formulated this problem as a regression task, and then we propose a novel convolutional architecture encompassing an SQD-LSTM block to estimate this regression function, and we added an SQD-LSTM block to the convolutional architecture so that we can model the global spatial dependencies, which are quite important in this phase unwrapping problem. And then we also introduced a problem-specific loss function, which can account for several conditions that we talked about in the previous slides, and also we achieved state-of-the-art unwrapping performance under severe noise levels, as well as you saw in the previous slide. And then we also noticed that our method expends significantly less computational time during inference compared to other methods, and that's and with that we can safely say that our network has was able to overcome some of the shortcomings present in previous methods. And in the looking at the future, we are hoping to apply this network to tackle phase unwrapping problem in QSM or quantitative susceptibility mapping, using MRI. And also we hope to do some more experiments involving formulating the problem as a classification task and seeing how network backbone would work in that formulation as well. And then we hope to extend our experiments to incorporate phase discontinuities as well, and that would that are some of the future work that we are intending to do in the coming months. So we would like to thank a few people and groups. So first up, Dr. Stephen Ballman from Center for Advanced Imaging Australia for introducing us to this exciting problem, and also Dr. Kan-Hyun Ryu from Stanford University for sharing the specifics of his work with us, which later inspired this work. And also, last but not least, the ICASSP 2021 Equalizing Committee for organizing the virtual conference during these tough times. So thank you very much, and let us know if you have any further questions. Thank you.